Okay, let's do this superposition of electric forces problem. And I'm going to do the whole thing from beginning to end and show all the little tiny steps. So I want to find the net force on Q2. This guy up here. So let's just think for a second about what the forces acting on it will be. So everybody's positive here. Q, everybody's glued down. Don't think about anybody's moving yet. 1 and 3 are stuck in place. They're both going to be either pushing or pulling on charge 2. Well, let's look at 1 and 2. We've got to look at each pair at a time. They're both positive, so they're going to repel each other. So Q1 is going to create an electric field at this spot that's going to push Q2 away. So we're going to have some force pushing directly up. Let's call this F12. That's the force from 1 acting on charge 2. 2 and 3 are both positive. They're going to try to push each other apart. 2 is going to try to push 3 down here. We don't care about that. We only care what's happening on charge 2. Choose a different color here. Maybe blue. 3 is going to try to push at some angle here. This is the force of 3 acting on charge 2. So if we draw a free body diagram for charge 2, remember you can move vectors around all you want. I'm going to have, let me stick with my color coding here. So Q2 is represented by a dot at the origin. I don't care that Q2 is not at the origin. This is a free body diagram. This whole thing is a physics 1 problem. So I have a force going up. That says F12. And then I'll have a force going at some angle. At some point, I'm going to have to find that angle. And we need to add these vectors together. To add vectors, we have to find the components. So let's look at F12. The force from charge 1 pushing on charge 2 first. Let's draw him by himself. He just pointed straight up. So we know, before we even go through the trouble of finding it, as a vector, F12 is going to be some 0i plus some number j. It has no x component, has only y components. Or if we write it in bracket form, it's going to look like 0, comma, some number, some positive number. It points up in the y direction. Okay, well, let's find his magnitude. Here we use Coulomb's law. Oh, that's a 2. Q2 over the distance between them squared. So that will be 8.99 times 10 to the 9th. Q1, these are in microcoulombs. So that will be 5 times 10 to the negative 6th. Q3 is 3 times 10 to the negative 6th. And the distance between them, we need to be in meters. So that will be 0.02 meters squared, because we were in centimeters. All right, let's type that in our fancy calculator. So 8.99. Now we can use the scientific notation button right here. So second EE 9, that means times 10 to the 9th. times 5 EE negative. That's your minus button right there. That's your negative button. Three EE negative 6 divided by, and what do we have? 0.02 squared. I can just use the squared button. Hit enter. So there is our force. We've got these two pretty close together. So the force is going to be relatively big. Okay, so that was 337. I'm just going to round that to a whole number here, newtons. So that vector there, that red vector, points straight up. We have to have this in component form. F12 as a vector will be the vector. We have the 0x component and this positive y component. Or if we wanted to write it in i's and j's, 0 I hat plus 337 j hat. Okay, now let's look at 3 and 2. So forget about 1 right now. We just care about 3 and 2. So at some point I'm going to have to find this angle right here. Let's call that angle alpha. I'm going to need trig. Let's go ahead and find that now. And let's do all this in red. No, we're on the blue vector. So blue is good. So let's go ahead and find that angle. So we could use trig here. I could use, say, tangent would be opposite over adjacent. So now I'm looking at F32. I had a 6 centimeter and a 2 centimeter. Here are my charges. I'm going to need that hypotenuse, and I'm going to need this angle. So tangent of alpha will be 2 over 6. So alpha will be the inverse tangent of 2 over 6. I'm in degree mode here, and I would highly recommend you be in degree mode for a problem like this. So that's 18.43 degrees. We're going to need the distance. Remember, we got, can't remember who I called 1 and 2. 2 and 3 up here. Here's Q2. Here's Q3. I'm going to need that distance in between them. That goes in Coulomb's law. So let's call this side C. C squared will be, I'll do it in centimeters and then convert. 2 squared plus 6 squared. So C squared will be 4 plus 36. That's 40. So C is the square root of 40. .32, that's in centimeters still. So in meters, C would be, move the decimal point 2 places, 0.0632 meters. Okay, so then in magnitude, we've got this vector. This vector, remember, vectors you can move around. You can put anywhere you want. When you're drawing a free body diagram, always start your vector at the origin. I've got this angle here is an 18-degree angle, 18.43 degrees. I need to find this x and y components. I'm going to call this side here F32x. This will be F32y. And then magnitude is the hypotenuse, and that's always positive. Magnitude is the hypotenuse, and it's always positive. Let's find the magnitude of the vector. That's just Coulomb's law. Coulomb's law tells you the magnitude of the electric force. That will be K Q3 Q2 over their distance squared. Everybody's in absolute value here because magnitude is always positive. So that's 8.99 times 10 to the ninth. What were these guys? 3 and 4 microcoulombs. And their distance was 0.0632 squared. All right, let's type that in our fancy calculator. 8.99 EE 9 times, what did we have? 3 times 10 to the negative 6. Remember, this is your negative button. If you hit that button, you're going to make your calculator mad. Times, don't forget your times also. 4 times 10 to the negative 6 divided by 0.0632 squared, 27. These guys were much further apart. What was our other distance? They were only 2 centimeters apart. Now we're 6 centimeters apart. Notice our magnitude went way down. So 27 newtons. That's the magnitude of the vector. I need the components of the vector. We add vectors component-wise. So now we just look at this triangle here. I'm going to draw that triangle a little bigger. Here's my x component. I'm going to drop the subscripts now and just call these x and y. Here's the magnitude. And this was that 18-degree angle, 18.43. So just looking at this triangle, I could say sine of that angle is opposite over hypotenuse. So just multiplying this magnitude over, that will imply Fy is the magnitude of the vector times the sine of 18.43 degrees. Similarly, cosine of that angle will be the x component over the magnitude. Oh, but wait, that's not quite true. See, we're using a reference triangle here. We always have to look at the picture to get our pluses and minuses. That will tell me how big this is, but I have to look at the picture and go, oh, well, look at that. That's a negative x component. It's pointing to the left. The y points up, so he's positive. The x, I have to put in that minus myself. So fx will be negative the magnitude of the vector times cosine of that same angle. See, this is really just a physics 1 problem. So now just plugging in all of our numbers, Fy, we're still on this 3, 2 vector, will be 27. That was our magnitude. It's right here. Sine of 18.43, and Fx will be negative. We know that from the picture. Cosine of 18.43. Okay, so let's get our fancy calculator out. 27. Make sure we're in degree mode. I already did that. And 27. I'll put the negative in when I write it down. Cosine of 18.43. 43. It's 8.54. And negative 25.62. Both of these are in newtons. We could check this, by the way. Now we know three sides of this triangle. We could do Pythagorean and see if a squared plus b squared does equal c squared. That would be a good check. But we don't need to do that right now. Let me make sure. Yeah, I did have that angle right. Okay, so then this vector, F32, the force that charge 2 feels from charge 3, points backwards here, in component form, would be the x, comma, the y. Or if you want to write it in I and j, negative 25.62 I hat plus 8.54 j hat. Now that we have both vectors, our net force is just the sum of our forces. And we add them component-wise. We add the x's and we add the y's. So here's my first vector, 0, 337. I'm going to add his x with his x. Let me do this now in black. So this is the net force. That's the first x plus the second x. The first y plus the second y. So that part's easy. Here, we could probably do that in their heads. That would give us a 15, so 345. Because 7 and 8 is 15. Yeah, I think that's right. Okay, so there's the net force. As a vector. We have to find this as a vector to be able to find his magnitude and his direction. Let's kind of draw him out. So he points backwards. He goes backwards, negative 25. And up 345. He goes way up. So that vector is going to point here somewhere. We could find his magnitude. We could use trig to find his magnitude if we wanted to, or we could just do Pythagorean. Let's do Pythagorean. His magnitude. Remember, I see students type this kind of thing a lot. They'll type in their calculator something like this. And they'll get the wrong answer because they put that negative in there and they didn't put this in parentheses. When you square a negative, that negative disappears anyways. When you're finding a magnitude, ignore the negatives. So I'm not even going to write that negative there. Okay, so real quick, let's type that in our calculator, and I could type the whole thing. Square root of 25.62. Where's my square button? Squared plus 345.54 squared. 346. Point, let's round, let's call that 5. Is that what I said? I want to make sure I write that right. 346.5 newtons. We have to have units there. So that's the magnitude of the net force. Now we got to find the direction. So anytime somebody asks you for direction, you can never ever just say, oh, it's at 20 degrees. If I told you to walk outside your house right now and walk at a 20-degree angle, you would say 20 degrees from what? Do I turn to the left 20 degrees, to the right, 20 degrees from the street, 20 degrees from what? So if we're going to find an angle, our answer, our direction is going to say something like 20 degrees from the y-axis, 117 degrees from the positive x-axis, something like that. So here's how I would do it. Let's call this angle beta right in here. So I'm just looking at that as a reference triangle. I don't even care about that negative. Just look at this as a triangle. Tangent of beta would be opposite over adjacent. Again, I'm not going to put that negative in there because I want to know how big this angle right here is in this triangle. So beta would be the inverse tangent of that. .54 divided by 25.62. 85.76 degrees. Okay, but that was this angle. I could, and it would be a perfectly fine answer to say the direction. That was really sloppy. Let me write that again. The direction of the vector is 85.76 degrees clockwise from the negative x-axis. That would be a perfectly fine way to give the direction. Anybody that knows the XY coordinate system could figure out which way to point. Most of us, though, would probably like to give this angle. This is kind of the more standard angle, but it's not necessary. I could find this little angle in here. It's going to be like 4.26 degrees, right? I could say 4.26 degrees from the y-axis. Or if I insist on giving the angle from the x-axis, well, I would just do 180 minus that. Let's call that angle theta there. This angle that's bigger than 90. So 180 theta would be 180 minus that thing we just got. So 180 minus, and I can just do second answer, 94.24. Degrees from what? From the positive x-axis. Now, should I say counterclockwise? Probably, but that one's actually not necessary. If you just say this, if I say 94 degrees from the x-axis, the assumption that everyone will make is that you mean you're rotating counterclockwise. That one kind of is standard. So like this would be okay. But if you wanted to be very specific, you would say counterclockwise. From the positive x-axis.